and they share an edge. That's the situation I'm considering. Now, consider the situation that there is no B where two red AB edges meet. Now, since there are three A's, if there is no B where two red ones meet, then each B has two blue AB edges meeting there. Because at each B, three AB edges meet, and if there are never two red ones, then there are always two blue ones. So from this fact that there is no B with this, I can conclude that each B has at least two AB edges that are blue. Now, the situation is a little bit more complicated. Now I'm going to have a look at the BB edges. Yeah? Now either there is no blue BB edge. Now that means that all BB edges are red. I have found my second monochrome triangle. It's BBB, which is red. Here I have AAA and there I have BBB. So I'm done. Suppose that this is not the case. Well, then there is a blue BB. However, I am in a situation that each B, in particular those two, have two different blue AB edges. So there are two blue AB edges meeting at this B, and there are two AB edges meeting at that. However, there are only three A edge nodes. So this pair and that pair share at least one A edge, one A node, and we have found a blue ABB. So we're done. This is a painful argument. Yeah? Why is it painful? Well, that is because we have to distinguish between the situation that the second one shares a side, the second one shares only a node, and the second one shares nothing. We have to make that case distinction. Another shortcoming of this argument is that it becomes extremely painful if, for instance, we would like to show that in the case of the complete 8 graph, I don't know, there are at least 3 or at least 4 monochrome triangles. I mean, you see the combinations exploding, and that's clearly not the way of doing it. Now, as I told you, the text from which I have, in which I found this argument, complicated matters by labeling the A's as A1, A2, A3, and the same thing with the B's, and then struggling with those subscripts. The trick of simplification, of course, is by not forming not introducing irrelevant distinctions. Now, the argument, the combinatorial argument that I showed to you, has everything wrong with it. You see? My very first argument was on the previous foil. I said, well, focus our attention on node X. Now, as soon as you name one of the 6 nodes, you destroy the complete symmetry between the 6 nodes. Yeah? So we should find an argument in which no nodes are named explicitly, if we wish to exploit the symmetry between the nodes of the complete 6 graph. Then we concluded that at least 3 of those 5 edges would have the same color, and I said, say red, thereby destroying the symmetry in the colors. You see, the whole problem statement is the same if you, it remains the same if you interchange red and blue. The whole concept of bichrome and monochrome is not dependent on either red or blue. We must find an argument in which we do not mention the individual colors. Because as soon as you do that, I say red, yeah, you destroy the symmetry between the colors. So, we had better head for an argument that doesn't mention individual nodes and that does not mention the individual colors either. Now, if you're not allowed to say red or blue, the simplest remark you can make that still does justice to the fact that there are 2 colors in the game is that if you consider a pair of edges, they either have the same color or are of different color. Now, question is, suppose that we are talking about pairs of edges, and we would like to consider pairs of the same, pairs of different color, homogeneous or monochrome or mixed. Yeah? So what is the simplest concept? Well, the simplest concept is not the homogeneous, is not the monochrome pair, because there are 2 types of monochrome pairs. There's the all blue pair and the all red pair. However, the mixed pair, 1 red and 1 blue, there is only 1 of them. So we are considering pairs of different colors. Secondly, because we talk about the complete 6 graph, somewhere the topology has to be taken into account. I do so by focusing my attention on pairs that have a node in common. And the central concept I'm going to talk about is therefore the mixed V. A mixed V is a pair of differently colored edges that meet in one point.